I love color palettes, and in this video I'm going to create a generative color palette system achieved through the interpolation of random pairs of colors. This is not my invention. This generative artwork was featured and described in the book Generative Design. It was there made through JavaScript and P5.js, and I found it a good idea to try and implement it in Max MSP. As you can see, clicking on the window generates new combinations of colors, and the position of my mouse determines the amount of rows as well as the quality, the resolution of the interpolation between colors. To be able to make this work, we will have to explore random color generation, interpolation algorithms, and of course jit.gen. Recreating basic generative artworks like this is an awesome way of discovering how to effectively use the basics of generative artwork tools in Max MSP. So let's see how this is done. Here I am back on the website for the Generative Design book. This book is all about creating generative artworks through JavaScript, or to be more precise, the P5.js library. All their examples and codes are available on their website, but today I am specifically interested in this one right here. As you can see, it seems fairly simple. It's just a bunch of colors. It's a color palette. More specifically, it is an interpolation between multiple colors. When I click on the screen, the colors are refreshed. There are new pairs of randomly generated colors, and the position of my cursor, of my mouse, determines the amount of rows as well as the resolution of the gradient, the interpolation from one color to the other. If we really want to, we can look at the code in the P5.js editor. So I can click this right here, and I have the exact same artwork. More or less, the colors are always random, of course. And the code can be viewed on the left. I am not planning on dissecting the code. If you're good with JavaScript or P5.js, you can always look at the code yourself. What is interesting is the possibility of different interpolation styles. So if I press 1, that is the default behavior, the interpolation between the pairs of colors are done through the RGB color space. But if I press 2, the same interpolation is done. The first and the last colors are the same, but it seems that the HSV color space is used. What that exactly means I'm going to get into as I try to recreate this using Max MSP. Now, in the JavaScript code, there is extensive use of for loops and creating and maintaining grid structures, but I think in Max MSP we are not going to need processes like that. Because in Max MSP there are already objects, while there is a data type that theoretically deals with grids, deals with data ordered in grid-like structures. And that is called the jitter matrix. You might have had experience with the world of jitter and jitter matrix, but more or less the jitter matrix is a possible representation of image and video data. It's one way of ordering a bunch of pixels or colors through a grid. You can of course do a lot of other things with jitter matrices, but for the purposes of recreating that specific generative artwork, we can think of jitter matrix as some kind of grid that we can visualize. And maybe the best example of this is through jit.noise, which is a jitter matrix, which is like a jitter matrix, but it generates random jitter matrices with random values in each cell, in each pixel. And to make jit.noise work, we need to give it some information. For example, the amount of planes, as in how many individual bits of data are going to be in each cell. And since we are working with colors, we want at least 3 RGB, the amount of red, amount of green, and amount of blue. We also need to tell it the data type, that is float32, and we need to give it its dimensions, its resolution. And for example, it can be 10 by 10, right? So the result of this can be viewed through the jit.window object. This is, I think, short for patcher window, so this is not an external window. We will make that later, but the output of jit.noise goes into this object, and then we can send a bang to jit.noise. And here we go. We have a bunch of random colors. Each time I click this, I get this nice image, a nice jitter matrix containing random colors in a 10 by 10 grid. And I can again do this all day, and I can have a lot of fun with all of these disco visuals I'm creating, but that is not the point of this artwork. The point is to first create a bunch of random colors around which we can interpolate and create our color palettes. So maybe instead of making this 10 by 10, we can make this 2 by 10, right? This can be our random color, I don't know, map that we can look up and interpolate between. Now we can think of these as pairs of random colors that we can interpolate between. That is the idea. But to make things even easier, I'm going to change the resolution once more from 2 by 10 to just 2 by 1. I just want a pair of random colors, something like this, right? And some random pairs of colors I find really nice, like this one is nice, for example, right? And some of them don't look so nice to my untrained eye, like, I don't know, like this one. There's not really a lot of difference between these colors, I feel. So let's try to use something like this. But let's start with this. Let's try interpolating between a pair of colors, and then let's see if we can extend that to a larger selection of random colors. So I'm going to create now a jitter matrix with similar specifications. So it's also going to have 3 planes. It's also going to have the float32 data type, and this is going to have a resolution of, let's say, 10 by 1, right? So instead of 2 by 1, I want this to have a resolution of 10 by 1, so that the first cell, the first pixel, can be this color, the first color, and then the last one can be the last color, and the colors in between can kind of interpolate between the first and the last one according to where they are in the jitter matrix. This kind of algorithm, this kind of way of thinking it lends itself very well to jit.gen. I know I use jit.gen in almost all of my visual tutorials, but this is just made for jit.gen. And jit.gen is one of the sub-programming languages or environments of Max MSP where you can define algorithms to process matrices very quickly and cell by cell. So whatever we define in jit.gen is going to be applied on each cell of the incoming jitter matrices. So this is very powerful, it's very fast, and it can be used to creating these kinds of generative artworks. By default, this little bad boy here has 2 inlets, so we can just plug our matrices in here. We can also create a button to send this currently empty jitter matrix into jit.gen, and to visualize the output, we can just take the first outlet and plug it into another instance of jit.window. All right, so if I click this, generate another pair of random colors, and then click this, well, I'm just going to get the first color because I really have not set any kind of algorithm in jit.gen, and its default behavior, let's see, is to just add up the 2 matrices, right? So we can delete this plus sign in the jit.gen. To access this, I need to lock the patch and double click on jit.gen right here. And then here, as I've said, I can delete this plus sign, and I'm left with these 3 objects I do need. In one, into, and out one. In one represents the information coming from the first inlet, into represents the information coming from the second inlet, and guess what? Out one represents the information that is going to come out of the first outlet of jit.gen. Now, when we are working with jit.gen, there is one thing we need to do in this case, and I hope I remember this right. We have to give it the attribute adapt 0. Now, in other cases, this is not necessary, but in this case, we are putting in to the right inlet a jitter matrix that does not have the same size as the matrix that is going into the left inlet. And normally jit.gen might try to kind of squish this and make it work in the context of the leftmost matrix, but we don't want that. We don't want it to adapt. We want jit.gen to take this matrix as it is and treat it as a 2 by 1 matrix. So if we don't have adapt 0 here, I believe we are not going to have the result that we want. Let's see, we can change it later if we want to. Now, what do we have to do? Well, I need to create an algorithm that is going to be applied on each cell, right? So I need to tell each cell which color it should be. And this color I'm going to define as a function of these 2 colors, right? So I need to select these 2 colors in my jit.gen algorithm. And I can do this through the object that is called, let me see, nearest pix, which performs a nearest neighbor sample on a matrix. It's a strange definition, but what it essentially does is that it receives a jitter matrix in its first inlet, right? And this is the matrix to sample, and in its second inlet it receives pixel coordinates. This means just integer numbers representing coordinates of pixels. This matrix is 2 by 1, right? So it is going to have 2 coordinates per pixel. It might look horizontal, but it's actually a 2-dimensional. Technically, it's 2 by 1. And the first one is going to have a coordinate of 0, 0, and the second one is going to have a coordinate of 1, 0, because we start counting from 0 in this instance. So to tell it this coordinate, we can create in jit.gen a vector. This is done through the vec object. For this artwork, it's a fancy way of thinking about lists. It's a fancy version of a list. It means other things, but you can think of it for this artwork a fancy version of a list. So when I declare a vector, I can give it values and I can say, well, this is 0, 0, and that goes into here. And now this nearest pix object is going to give me the values of this color. I can do the exact same thing. I can get my second color, another nearest pix, and the vector of 1 and 0. That is going to be the coordinates. The same input goes here, and now this guy right here is going to give me the values for the second color. Right, so I now need a way of mixing or interpolating between these colors, and I can do this very easily through the mix object in jit.gen. I believe this object does not exist in regular max MSP. And what it does is that it performs linear crossfade of inputs. It has 3 inlets. The first 2 inlets are the 2 values we are going to interpolate between, in our case 2 colors. And the third inlet is more or less the interpolation factor between the inputs. So it's going to be a value between 0 and 1. Value between 0 and 1, a normalized value, as some people call it. Right, so if this is 0, we are just going to get the first value. If this is 1, we are just going to get the second value. But if it's a value between 0 and 1, we are going to get something between these 2 values, aka a mixture between these 2 colors. All right, well, how are we going to define this value then, right? Because this value should differ between from cell to cell. This must be different between cells. And we can do this through pulling up the normalized coordinates of the input matrix. The norm object does that. And its behavior's default and only behavior is to give us the coordinates of the first matrix coming into this object, right? So we are going to get the coordinates of this matrix right here. And these are not pixel coordinates, these are normalized coordinates, so they're going to go from 0 to 1. So the cell number 0 is going to have the value 0, cell number 5 is going to have the value 0.5, and cell number 10 is going to have the value 0.9, I believe, or it might go all the way up to 1. I don't know how it's exactly spaced, but in any case, we have to keep in mind that this is a 2-dimensional matrix. This is 10 by 1. So norm is going to give us pairs of coordinates, or 2 values per coordinate, just like these vectors right here. And I only need the x coordinates, so I'm going to use the Swiss x object to isolate the x coordinate here. That's going to go into the last inlet of mix. And now whatever the output is, that can just go into out 1. There we go. So this should be enough. Let's see if this works. If I generate a random pair of colors like this and then click this button, yes, there we go. The matrix goes in here. It goes through jit.gen. It uses the information coming from jit.noise as some kind of lookup map or an interpolation map. And as you can see, it interpolates perfectly between these colors. It's just beautiful. I can even create this nice button that is connected to the other buttons. And as you can see, no matter what the pair of random colors are, we are just getting the same kind of interpolation between colors. Well, that's a bad one. Let's get a good one. Let's get a good pair of colors. Yeah, this one's good. So yeah, look at this. Just perfectly in 10 steps, I believe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps. And this is something we can dynamically change because we never put the number 10 in our jit.gen patch. We were just using norm, right? So I can make this, I don't know, 5 by 1. And then I'm going to have 5 steps in my color interpolation. Or I can do 50. So this can be 50 by 1. And then I'm going to have 50 steps. Then it looks very smooth. I can even go 1000. There can be 1000 steps of interpolation from one color to the other. So right now it's all dynamic. And that is exactly the way we want it. All right, now what we want to do is to kind of expand this, right? I want it so that it will work with, let's say, a lookup matrix or some kind of random inputs that is more than 2 by 1, right? So this is 2 by 10, this is what we want to work with, and this has a bunch of pairs of colors. But right now, even if I change my main jitter matrix, the dimensions of my main jitter matrix to something like 10 by 10, I don't think I'm going to achieve the result I want, because the interpolation is always going to be between the first pair of random colors. And that's because I never told my jit.gen algorithm to look at the other pairs of colors. If I go back into my jit.gen, you can see the coordinates I use to pull up the colors to interpolate between. It's just the same. It's always 0, 0, and 1, 0. And in this case, when I'm trying to have multiple pairs of random colors, I do want to make it so that the y coordinates of my incoming matrix, my jitter matrix, not the noise, the jitter matrix, has an effect on the y coordinates of the coordinates that are being used to pull up the random pairs of colors. So how can we do that? Let's see. Well, we do have the second inlets of these vec objects, right? And this lets us replace the zeros here. So instead of 0, 0 and 1, 0, if I send in a 5 in these second inlets, this can be 0, 5 and 1, 5. This is something we can dynamically change. So what I can then do is, let me think. Yeah, so I can pull up the pixel coordinates of my incoming matrix, right? So just like norm, I can just create an object that's going to give me not the normalized coordinates, but the pixel coordinates. And I can do this through the cell object. It's going to give me the cell coordinates of the input matrix. And again, this is 10 by 10, or matrix is 10 by 10. So cell is going to give me 2 coordinates per cell, right? The x coordinate and the y coordinate. But I just need the y coordinates. So very much like the norm and Swiss x here, I can create Swiss and give it the argument y this time around. And taking this, I can plug these into the second inlet of these vec objects, and that should be enough. Yes, look at this, beautiful. We finally have exactly what we wanted, and it wasn't so difficult, right? It's just a matter of figuring out the coordinate systems and creating and implementing the right kind of algorithm. Now, each time I refresh this, I just refresh the noise and I send jit.matrix through jit.gen, I'm always getting these nice gradients, these nice interpolations through the pairs of random colors. Now I can play around with the dimensions of my main jitter matrix. So this can be, I don't know, 10 by 3. And what is going to happen if this is 10 by 3? Well, I'm just going to get the first 3 rows, the first 3 pairs of random colors. Right? I can make this 5 by 4. Right? And again, I'm going to get the first 4 pairs of random colors, and so on and so on. Now, I do want to implement this in a jitter window or a jit.window object, as we're going to see it in a bit. But before that, I do want to figure out this matter of a mode, or different modes. If you remember right here, there were 2 different modes of color interpolation. The default one was the RGB interpolation. That's what we did. We are taking the RGB values of each color and we are interpolating between them. But then there was the second mode, which also is beautiful in my opinion, that interpolates between the HSV values of these colors. Right, and this is another way of representing and thinking about color. Instead of the amount of red, green, and blue that is used to create a color or represent a color, HSV uses the hue, saturation, and the value, more or less the brightness of the color, in order to figure out how it's represented on the screen. And when this mode is used, the interpolation between the colors essentially ends up as this travel through the color wheel, travel through all the possible hues until we arrive at our target color. Now, the thing is, how are we going to implement this in jit.gen? Well, there are 2 objects that are simply key in implementing this. And these are called RGB to HSL and HSL to RGB. Now, these objects are pretty simple. I think what they do is written on the can, it's written on the description, well, the name of the object. RGB to HSL takes color information, things like what we get from nearest pix in this instance, and turns it into a representation of color through HSL, which is not so different than HSV. And HSL to RGB takes information that represents color in the HSL color space and converts it into a representation of color through the RGB color space. So if we want to do this, what we can do is to take the RGB to HSL and put it right after nearest pix, both nearest pixes. Or would it be nearest pixi? I don't know. Anyway, doing this, we are taking our color, we are turning it into HSL values, we are mixing between the two of them as they are represented as HSL values, and after it comes out of mix, what we do is we simply convert it back to RGB and then send it out. And if we look at it that way, maybe we can increase the dimensions, like let's make this 25 by 10. There we go. I don't know if this is immediately apparent, but maybe you can see the interpolation being a bit more rainbowy. The colors are really going through different hues. They're going through the rainbow as they interpolate between the pairs, the two ends. And I do find this more beautiful, I really do. And I would probably use this for my own generative artworks, but since we are implementing an already existing generative artwork, I do want to have the option to switch between different modes. And we can do this through the selector object. The selector object in jit.gen lets us select between a number of inputs. So here is what I'm going to do. I'm going to create the selector object. I'm going to give it the argument 2. So we are going to be able to select between two inputs. And here is my plan. I want to have two options for the two inputs to the mix object. And these options, these two options, go into the second and third inlets of selector. The first option is whatever comes out of nearest pix, right? Whatever comes out of nearest pix is my first option, and the translation, the conversion of the output of nearest pix to the HSL value is my second option. There we go. So the first inlet of selector lets me choose between these two options. It lets me choose between these two options, and whatever is chosen, it will be sent from the outlet of selector. Similarly, when I have the output, when I have the output of my mix object, I again want to select between two options. Either just whatever comes out of mix, or the conversion of whatever comes out of mix to the RGB color space, and that would go into the third inlet of selector, or second choice. And again, whatever our choice is, that goes into out one right here. So now the first inlet, or the first inlets of these selector objects, will let us choose between either the RGB colors or the HSL colors and the translation of those HSL colors back to the RGB color space for the outputs. The selector, this inlet of selector needs either 1 or 2, and maybe we can set this from outside of jit.gen, since this does need to be a dynamic parameter. And I'm going to do this through the param object. So param lets me declare a parameter, and I will say I'll give this parameter a name. Let's call this, I don't know, mode. That's how it was called in the original sketch, right? And let's give it the default value 1. Param mode 1. And the outlet of this guy goes into the first inlets of all these selector objects. There we go. And I think this is it for this algorithm. Maybe I can clean this up before I upload it on GitHub, but this is more or less it. Now, going back into jit.gen, well, now I have an external parameter, so I can simply make messages like mode 1 and mode 2 and put these here. So let's see, if I change this to mode 1 and if I click this button without refreshing the random colors, well, here I get the RGB interpolation. If I change the mode 2 and press this button again, then I'm switching to the HSL interpolation. This is very cool. Now, the last part is to create a window, put this into the window and make it interactive based on the position of my cursor while it is on this window. This is no easy task. It's, again, deceivingly easy, as in it's not easy at all. But we can pull through. I think we can do this in an amount of time that is less than 5 hours. So the object I'm going to use is jit.window. This is going to display jitter matrices in a window. I can give this an argument, a name. I can call this whatever I want, and I'm choosing to call this color time because it is time for colors. I will also give this some attributes such as floating set to 1, so the window will always float above the patch as I edit the patch. And this is very important, I'm going to give it the attribute idle mouse 1. This attribute, idle mouse 1, is going to let me look at and receive information about the mouse while it is on the screen. Okay, so what do we need to do here? Well, I need to send jitter matrices to this window, right? So I'm going to take the output of jitgen, put it into this jit.window, and now when I click this button, I'm just getting the stuff in my window. It doesn't matter what the size of my window is or what the aspect ratio of my window is. It will always fit in the window. Right? Now we want the mouse information while it is over the window, and idle mouse 1 does indeed set that, but to receive it we need to look at the second outlet of jit window. And we can simply visualize this information through a message box. Let's see. While my mouse is on here, it does send out a message that says mouse idle and then 2 numbers representing the x and y coordinates, pixel coordinates of my mouse in the window, and then a bunch of zeros. And if I click on the window, well, I do get this little 1 after the coordinates. It says mouse, not mouse idle, but mouse, the coordinates, and then 1 if I'm pressing and holding the button, and if I'm releasing it, it gives me 0. And in the installation itself, in the artwork itself, that is used to refresh the colors, right? So that is used to more or less press this specific button, the button that goes into jit.noise. And maybe we can start with that. Let's create a route object and let's give it the arguments mouse idle and mouse. Not moud, but mouse. There we go. And now the second outlet is going to give me the information that is sent out if the beginning of the message is mouse. You can see it right here. So now I want to isolate the third element in this list, because this third element, 0 or 1, represents if I'm clicking the window or not. And I can do this easily through the zl.nth object. Right? I need to give this object an argument, which index number in the list am I looking for. This is 1 based, so 1, 2, 3. I'm looking for the third element. So zl.nth with the argument 3 is going to give me either 0 or 1, depending on if I'm clicking in the window or not. All right, to make sure the repetitions are not reported, I'm going to use the change object, and then I'm going to use select or cell 1 to make sure a bang is sent out each time there is a change from 0 to 1. Let's see. Yep, now when I click in the window, I'm receiving a bang. This was all a roundabout way of getting a bang when I click on the window. And now I want to send it here, and I can simply do it like this, but this looks incredibly ugly, so I'm instead going to create a send-receive pair. So send, and let's call it new colors. Let's send it here, and then, oops, instead of send, I'm going to create receive new colors, and that's going to go in here. And now I can refresh my colors each time I click on the window. Though this doesn't always lead, or in this case it really doesn't lead into the colors in the window changing, because for that I would need to either click on the main button here, which I want to avoid because these two are separate processes and I don't want to automatize that, or I can simply click here and keep clicking here and click here again and again and again forever. Or I can just create, let's say, the metro object, give it the argument 33, and give it the attribute active set to 1. This is the same thing as connecting a toggle to the metro object and turning it on. So it's like the metro object is automatically on, is already functioning if it has the active attribute set to 1. And if I do this now, just very quickly, every 33 milliseconds, this matrix is being sent through JitGen, and then I'm receiving the resulting image in my JIT window. So I can now click on the window and get new pairs of colors as much as I want. All right, but that's not it, is it? When the mouse is on the window, I could also see that in the original sketch, the resolution of the interpolation changes as well as the amount of rows. So how am I going to incorporate this? Well, I need to think about what I am changing in this case, and what I'm changing is the dimensions here, right? So the resolution would be the horizontal dimension, or the length of the horizontal dimension, and the amount of rows would be the y dimension, the length of my jitter matrix. So to dynamically change this, I need to do something yet again tricky. I need to normalize my mouse coordinates. These are normally pixel coordinates, and I want these to go from 0 to 1. Why do I want this? Because the size of my screen could change at any moment. I want to make sure that this is reactive to the size of my JIT window. So to do this, I need to take these coordinates and I need to divide them by the size of my JIT window. So let's start by getting the size of the window itself. To do this, I'm going to use the getAtter object. And as an argument, I'm going to type in the attribute whose value I'm trying to pull through the getAtter object. In this case, it's size. And then I need to connect the middle outlet of getAtter. This is a bit backwards, I know, but I need to connect the middle outlet of getAtter to the inlet of JIT window. And when I do this, the first outlet of getAtter is going to give me, there we go, the size of my window as I'm changing it. All right, and then I know that the first outlet of route is giving me the mouse information, more specifically the coordinates right here. So I'm going to slice out the first two elements in this list, and then I'm going to divide them by whatever the current size of my window is. So zl.slice is going to do the slicing. zl.slice2 is going to slice the first two elements in my lists, as you can see. And then I'm going to use the vexper object. This is going to let me evaluate a mat expression for a list. And my expression is as such. I don't want to get too much into the syntax, but $F1, so the float numbers coming into the first inlet, divided by $F2, the float numbers coming into the first inlet. I know these numbers are not float, but if I treat them like they are float, they are calculated as float numbers, and the result is a float number. I want a float number between 0 and 1. So let's put it like this. Let me see, there we go. We have to make sure it's clean. So the first inlet is my coordinates, the second inlet is the size of the window. And the result should be a pair of numbers. Let's see. There we go, a pair of numbers between 0 and 1. The first number is 0 if I'm all the way to the left, and it's very close to 1, like 0.99 if I'm all the way to the right, and the same thing goes for the second number. When I'm at the top, it's 0, and when I'm at the bottom, it's very close to 1, but not quite. All right, so since we have these pairs of numbers, we are almost there. We just have to unpack these, unpack 0, 0, and then I need to scale these numbers. Oops, I accidentally clicked on the window here. I need to scale these numbers to the ranges that I want. So let's see, for the resolution, I want it to go from 2, if I'm all the way to the left, to 100. I can simply multiply the number, but I just love the scale object so much, I'm going to use it. So scale 0 to 1, 2 to 10, no, 2 to 100. This is going to be the case for my X position. And the second one, from top to bottom, I want this to go from 1 all the way to 10, right? So the incoming range is from 0 to 1, and the outgoing range should be 1 to 10. There we go. And then that's also going to give me the right float numbers. Yes, perfect. And now let's create the kind of message we need to change the dimensions of our jitter matrix. So for this, I'm going to use pack, and I'm going to give it the arguments dim, that's the first part of the message we need, and then 0, 0. Those are going to be the dimensions of our matrix. Right, so this 53.2 can go here in the second inlet, so it changes this 0. The first inlet is dim, the second inlet is the first 0, and the third inlet is the second 0. Now you might be thinking, well, these are float and don't we want these to be integer numbers? Well, the fact that there are no dots for the arguments of pack will make sure that these are automatically converted to integer numbers as they are going through the pack object. As you can see, I formatted the message I want, dim, and then two numbers, the width and the length of my jitter matrix as I want it to be. And this should go into my main jitter matrix right here. And again, I can just like plug it in like this, but this looks so ugly. I would rather use yet another send receive pair of objects. So let's say send new dim. Dim is of course short for dimension in this case. And receive new dim. Put it here. And now it should be working. Yes, look at this, beautiful. I can move my cursor as much as I want around the window, and just like the P5 sketch itself, each time I click, it's going to create new variations. Its resolution is going to change as I go from left to right, and the amount of rows are going to change as I go from top to bottom. If you have good eyes, you might have noticed that the maximum amount of rows is 9, because I will never reach 1 in my coordinate, and I will never have the value 10 as a result of scale here. But to fix this, I can just make this go from 1 to 11, and then I'm going to have, I believe, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pairs of colors. Beautiful. All right, so there you go. I think this is a really, really cool experiment. It's a really cool generative artwork, and it can be used in all kinds of visual and audiovisual situations where you need a dynamic palette. You can try to work with this further. I would recommend trying to go beyond the bounds of the dimension. So what happens if we go further than 10 for the length? What if we go to a ridiculously high number like 1,000,000 for the width? Because these have implications for the generation of palettes. And you can also consider using not noise, but some kind of other visual input for our pairs of colors right here. In any case, I hope this has been useful to you. I hope you create a lot of beautiful artworks using this, and thank you for watching.